Here we go again. EIGRP. It's probably one of my favorite ones actually. So hope you enjoy. Might also be a long one today. So here we go. What are we gonna do? Describe the basic features of EIGRP. Describe the types of packets used to establish and maintain an EIGRP neighbor adjacency. That's probably the worst part. Describe the encapsulation of EIGRP messages. Configure EIGRP for IP version 4. Then configure and verify it for IP version 4 around a small routed network. Explain how neighbor adjacencies are formed using EIGRP. Explain the purpose of the metrics used by EIGRP. Explain the operation of dual, that's the algorithm, and the use of the topology state. Describe events that trigger EIGRP updates. Compare characteristics and operation of EIGRP for IP version 4 and to EIGRP for IP version 6. Then we're going to configure it for IP version 6. Verify EIGRP for IP version 6 in a small to medium sized network. Woo! Here we go. So we have this class activity on classless EIGRP. So classless just means it's going to send our routing prefix rather than over here the 10's using a 16. The 172.16 is a classful routing prefix. Anyways, we're not going to worry about this class activity unless you want to. Go ahead and do it on your own. Alright, features of EIGRP. Okay. Well, it's super neat. Alright, it's IGP. We already knew that, right? We knew it was an IGP. We knew it was this thing. Now, where is it? It's a distance vector routing protocol. We knew that. It is usually called, I don't know, a hybrid distance vector routing protocol or a advanced distance vector routing protocol, because it actually shares some of the stuff of OSPF. We'll see that it has similar things, probably more similar things than RIP, but it's not quite a link state, right? It's not giving the whole map. It's still like a Mr. Rogers protocol where it bases most of what it does on its neighbor information. Okay, but yeah, what's it called for IP version 6? EIGRP for version 6. Maybe the easiest one to remember since it's the same name. You know, OSPF was version 3, RIP is NG. I guess EIGRP holds the same as ISIS and BGP. So we just have to say for IP version 6. Let's see. We'll just keep going. There's probably some good details on the history. Here we go. Diffusing update algorithm, dual. That's the algorithm we're going to be using. It's much different from before. We had OSPF. Its algorithm was Dijkstra, but we are going to see some of the things like establishing neighbor adjacencies. It's going to be the same as OSPF basically, except we're not going to be in areas. We're going to be in autonomous systems. Our layer 4 protocol is this thing called RTP, Reliable Transport Protocol. Okay, so RTP is not real-time transfer protocol, which is VoIP. I think it's real. There's another RTP for VoIP, so don't get confused with this RTP. This RTP is, so like OSPF uses layer 4 protocol of OSPF. EIGRP uses a layer 4 protocol of RTP, and so RTP makes sure it's better than TCP, I guess, for making sure that this thing gets going. How does EIGRP work? It uses partial and bonded updates. These terms mean, unlike RIP, EIGRP does not send periodic updates. The route entries do not age out. The term partial means that an update only includes information about the route changes, such as a new link or links becoming unavailable. The term bonded refers to the propagation of partial updates that are sent out to those routers that the changes affect. So similar to EIGRP, right? So instead of a timeout, we still have hello timers and all that, just like EIGRP. Here's one unique thing, which I believe OSPF only does unequal cost load balancing. On EIGRP, we're going to see our metrics are crazy. They're very big, and so equal and unequal cost load balancing, because it's rare that we have a route to two places that actually is going to have the same distance. You'll find out why. Typically because our base unit is bandwidth and delay, unless we change the other K values, which we will be talking about in a second. Alright, so here's the strange thing. Protocol dependent modules. Alright, so basically EIGRP runs in an AS. We can have different ones for IP version 4, but we can run EIGRP on one router. We can run it for both IP version 4 and IP version 6. They're different, and so what it's saying here is in EIGRP, a successor is the route in the routing table. A feasible successor is the backup route. And so, yeah, I don't know. We can just have different things. I believe that's what they're saying here. Yeah, basically it's just saying, if we look, it's talking about IPX and stuff, so now we only have IP version 4 and IP version 6. So what it's saying is the protocol dependent modules, what protocol is it dependent of? Well, we have a table for IP version 4. We have a table for IP version 6. If we're running IPX or AppleTalk or something, apparently we could have those things different, right? And so the PDMs are responsible for specific routing tasks for each network layer, including maintaining the neighbor and topology tables of EIGRP routers that belong to the protocol suite, building and translating protocol-specific packets for dual, interfacing dual to the protocol-specific routing table, computing the metric and passing this information to dual, implementing filtering and access lists, performing redistribution functions to and from other routing protocols, redistributing routes that are learned by other routing protocols. So specifically, the most thing he talks about here is this dual, which is the algorithm, remember. So it says basically each PDM will run its own little dual, and so we don't have to worry about IP version 6 failing and taking down IP version 4. I don't know, it all makes sense in my opinion, but yeah, each PDM is going to have a neighbor table, okay, and all that. So here we come to RTP. Alright, so what's important about RTP? Well, it's not TCP or UDP. This is what EIGRP uses, and the most important part is down here, right here. RTP can send EIGRP packets as unicast or multicast. Multicast EIGRP for IP version 4 use the reserve IP version 4 multicast address of 224.00.10. Okay, now that's something that I can guarantee you is going to be on the test. And then so for IP version 6, what's the multicast going to be? Well, FF02, meaning link local, IP version 6 multicast, because as we'll find out in IP version 6, all the routing updates, just like OSPF for version 3, the routers talk to each other through their link local addresses for all updates. But anyways, FF02::A, or the same thing as 10. So if we can remember EIGRP is 10, we're good to go for these numbers, right? So multicast with 10 and multicast for 10. Routers with 10, I guess. So FF01 would be all nodes, I believe, link local, whereas the FF02 is routers, link local. Okay, so it's happening. Here we go. So this might be important. At the application layer, we have the neighbor table, the topology table, and the routing table. Okay, I guess that's happening at what we'd call the PDM. Alright, so our show commands showing our neighbor table, our topology, and our routing. It's the application, probably the actual application going. How is it handed to each other? Well, through transport and RTP, and then we have our layer 3 protocol, right, our network protocol, internet protocol, which is either IP version 4 or IP6, and then we can either have LAN or WAN connections that we're learning at the layer 2. Alright, authentication. I guess we talked about this on OSPF, but Alright, so all this authentication means is we can put a password. Note, authentication does not encrypt EIGRP routing updates. Alright, so what is this actually doing? It's just, we can authenticate, we can put a password, so we use a clear text password, or we could use an MD5 hash password. It's not hashing, it's not encrypting our routing updates, right? It's just making it so we can't join the autonomous system, right? So all these guys are in the same autonomous system, meaning they share updates, kind of like an area. And if you're not authenticated, you can't join. Alright, so here's our type of packets with the EIGRP. Hello, use to discover other EIGRP routers in the network. Shocker, huh? Acknowledgement, used to acknowledge receipt of any EIGRP packet. And now here's the three important RTP ones, right? These are all RTP, but update, convey routing information to known destinations. Query, used to request specific information from a neighbor router. Reply, used to respond to a query, right? So updates are going to happen when they send, like, on a change, I would say. Query is when they're trying to learn updates, and I would say reply is when a router replies to that query. Messages are sent over. Okay, neat. If we couldn't figure this out, it's a packet. Alright. So, hello sent with unreliable. Alright, so hello is not RTP. Unreliable deliver. We don't make sure it's there. Multicast on most types of networks. Update packets sent with RTP. They can be unicast or multicast. So multicast would be like if we were updating. The cool thing about multicast, right? We have 3 routers. Right? I need to shrink my pen here. Anyways, these are routers. This router can send one multicast packet and hit both of these, right? And so that's what makes it fun. That's what just makes it just a great time with the multicast. The same bandwidth. That, or we can do a unicast to one router if we don't want to update everybody. Reply, sent in response to an EIGRP query. Is RTP is always unicast, right? Because somebody has queried. Now the query can be unicast or multicast as well, so there you're looking for information. Alright, so the thing about hello packets, well, they're sent on this multicast apparently. And so then they go in the important stuff. EIGRP routers discover neighbors and establish agencies with neighbor routers using the hello packet. On the network, on most networks, EIGRP hello packets are sent multicast every 5 seconds. As we can see, that's what this goes. So anything faster than a T1, our hello is 5 seconds, and the hold timer is 15. If it's slower than that, they're sent every 60 seconds, and the hold timer is 180. Hopefully no one has to go with a network that's slower than 1.5 for 4 megs in this day and age. So I think this is kind of an older thing that you're seeing. What is the hold timer? It is used to determine the maximum time the router should wait to receive the next hello before declaring that neighbor is unreachable. Okay, so those hellos are also giving us I don't know, basically the dead timer as well. So here we go. It's showing us how our updates and acts acknowledge. EIGRP sends an update. Boom, boom. It's multicast, so it hits all routers, and then sends back. These routers acknowledge that they have received the update, and everybody's happy. Dual uses query and reply packets when searching for networks and other tasks. So if you lose connectivity, Dual says, hey, does anybody know another route to this network up here? As we can see, there isn't one, so the reply would be probably, hey, nope, I only knew the way through you. Encapsulating EIGRP. Alright, so we're going to talk about that. And what it says is it starts out with every multicast 01005E, and hopefully you figured out the last number because it's going to be what we call 10, right? We talked about that earlier. So 0A is 10, right, in hexadecimal. So it's 01005E 000A on the layer 2. Then we go to layer 3. We got our multicast of 224.0010. It's IP version 4. Then we have the code that tells it whether it's a reply, query, all that RTP, or maybe it was just going to be a hello. And then finally, the other parameters, I guess. So the TLVs. Does it have anything else on TLVs? I don't know. It looks like it tells it whether it's a local EIGRP route or an external EIGRP route. Alright. So it's showing us the opcodes. Shown before. The autonomous system number in EIGRP is probably the most important number. It's what allows us to form these neighbor relationships, so that's probably why it's important in that part. So then we come to the K values, right? And so our K values are, let's see, we have bandwidth and delay by default, and then so it's K1 and K3. K1 is bandwidth, K3 is delay. Then we have, let's see if I can remember off my head without looking here. Maybe you can find them. Bandwidth, delay. Alright, I'm going to remember. It is bandwidth, delay, reliability. I don't know. It's the things that you do when you do a show interface. It shows you, bandwidth, delay. I think maybe MTU is one of them, and finally reliability, something like that. Yeah. Well, hopefully it tells us here in a second. So go over here. Oh, is this it? Here we go. Delay, bandwidth, MTU, load, reliability. That's our 5. Delay, bandwidth. Anyway, so apparently those are in the IP internal TLV routes. This is gonna calculate it. So what these K values are doing is calculate our metric. And so the more we put in there, the bigger our metric's going to be, for one, because it's going to be a multiple. And then not only that, it is also, the K values have to be the same on all devices. Like if we're going to enable more, we're going to enable on all routers. Otherwise, it's not going to form an adjacency. So what do we have? What else here? Probably a good thing to look at. I guess we have internal route versus external route. External route has a whole lot more, probably because it could be EIGRP, static route, something outside of our local EIGRP autonomous system. Alright, EIGRP network topology. So in this topology, just like with OSPF, we're going to have to use the bandwidth command on the serials. Is that what it's telling us? Oh, they didn't there, they didn't there, they didn't there. Anyways, I would use the bandwidth command so it calculates it a little better, but I guess they're just showing us that. Now how do we program it? Okay, so the autonomous system is the EIGRP routing command. So we say router EIGRP autonomous system and then a number. Okay, so that number can be 1, not 0. We cannot use 0 in this place. Okay, just like with OSPF, that first number cannot be 0. 1 to 65,535. And all of the routers in our domain have to also be in that same autonomous system. That's what's going to allow us to form a hello. Here's the commands where they put it in router 1, and they did it on all 3 routers. Okay, so then what do we have to do next? Well, just like on OSPF, we have to put in the network command. So they did a router ID. Oh, they're putting the router ID in. Okay, so we did that in OSPF as well. Router ID is a little less important. Basically, they want you to do this because when we have to do, I don't know, it just says it's more important OSPF, right? So router ID is more important in OSPF. The reason they're doing this is because in EIGRP for IP version 6, it needs the router ID. So why not use it right now? Alright, but it just identifies the router in the same way. You know, we can do 1.1.1, 2.2.2, 3.3.3, or it'll go into our loopbacks and all that, but yeah, it's not selecting a DR or anything in EIGRP like it was in OSPF. So they give you the router command. Why do they not give us a network command yet? Okay, finally we get to the important one. So we did the most important commands are saying router EIGRP1. Alright, so we did that on each one of these guys. Then these networks, we gotta include them, just like we did with OSPF, but easier because we say network and the network address. If we don't want it to send a default, we also have to say no auto summary. If we don't want it to automatically summarize these, because that's what EIGRP will do. So that would be another command. Maybe they have it. Nope, just network. Just network. Okay, but anyways, when we do that, we'll see this adjacency form and everything runs. So no wildcard mask unless, here we come, wildcard mask. What is it used for in EIGRP? It's to only allow certain networks to perform, to use the network command. So like if we had multiple networks broken up of 10, like on this router, right, we have this is a 10 interface, this is a 10 interface. If we only want one participating in EIGRP, we say network, 192.168.10 dot, whatever it is with the wildcard, right? Or we could just go 192.168.10.0 and it would include both of those. And that's kind of what they're showing there. So it's to exclude certain routes, right? So what do they say about it? Specifically enables EIGRP on a certain interface. So if we only want to specifically enable it on a certain interface, passive interfaces, we put those on the LAN where we don't want routing updates to go out, right? It helps secure it. Helps. We don't need them out there, so don't put them out there, right? So same thing is with OSPF. Verifying EIGRP and examining neighbors. Okay, show IP EIGRP neighbors, shows the neighbors' addresses, shows the interface we're connected to, and the hold down timers. So the hold down timer goes to 0. I think this is pretty common. We're going to declare that neighbor down, try to find another group. So all of this is pretty easy. we want to get to some verifying commands. EIGRP's default AD, we already know, is 90. The external AD is 170. And a summarized is 20, actually. Right here it shows us what K values we're using, where the ones are. So remember, K1 and K3 are our defaults, just bandwidth and delay. We don't have automatic, or we have no auto summary on, right, which is what I told you. So that command is just, I didn't see it, but hopefully, maybe it's on, it might have been somewhere. Let's not use that one, we'll use black. But it's just inside of router, EIGRP1, no, auto, I believe it's dash, summary. So what that's going to do is actually not automatically summarize neighbor routes, right? So if we're doing classless, we probably want to do that. Because there's not very many times, I don't know. We're network administrators. We don't want to just leave it up to doing automatic things. We can do it better. We might put in, so I don't remember if it's in this chapter or the next one, but we can also put in our own summary routes. So that's what we're waiting on here. Alright. So as you can see, now this is what I'm talking about with a large metric is if you see our AD is 90, but then we have like 2, 1, 7, 0, 1, 1, 2, right? That's our metric, is that second number. And it's a big one. It's a big one. So how do we get there? Well, hopefully this will help us in the future. Oh, what else is it showing us? If we have 2 right here, that means that they are load balanced, and these ones are actually equal load balanced. I'm guessing the next ones we're going to see, this would be unequal load balanced, and we can see that from, let's go back to our show IP protocols. Maximum paths, that means it will equal cost would be 4, and then we use the command I believe it is variance, so we use a variance of how unequal we want it to be, and we can load balance on like unequal, I believe 8, and then equal load balance. They change it based on OSI, but I believe it's 16 that we could max out for equal paths. Let's see. Does it tell us in here? Oh, it just says these are going to be discussed later in the chapter. Okay, great. Okay, so how are EIGRP neighbor adjacencies formed? As we can see there, we do our router EIGRP, we do the network command, and then that allows us to start sending hellos out that interface. So as soon as it does that, it says, hello, I'm in this area, and if they're both, if they can form a neighbor adjacency with each other, because they're in the same autonomous system, have the same K values, are in the same network, that kind of thing, they send all their other routing information. And then they send a hello to say, anybody else out there, right? Alright. So, first thing we did that. Then, after the hellos and the updates and another hello, there's acknowledgement of getting the routing information, and then the other router will send an update to then be acknowledged by the other router, right, that it received its routing information. And then we're converged, right? After we have an ACK on both sides, we are converged, meaning we know all routing information that these two routers could know. Alright, feel free to do this activity to make sure you know it. Alright, so now the metric. How we calculate it. This is a good one. So to find our metric, we multiply K1 bandwidth plus the K3 bandwidth divided by 256, right? So K1 multiplied by the bandwidth plus K3, the delay, multiplied by 256. Sorry, I said divided. Alright, and so if we were using other ones, they do different things. Let's see, so if we're doing load, we start getting divided, but then, so we divide 256 minus the load, then we add plus, but as you can see, I don't know how you would ever, don't worry, you're not tested on this. All you need to know is K1 and K3 are the delays, and you need to know that there's a bandwidth, another bandwidth. Here we go. So we have bandwidth, load, delay, reliability, and reliability. That one of those is wrong, right? There should be something besides reliability. I guess not. I guess that's why I could remember it. Represents reliability, so bandwidth the slowest among all of the outgoing interfaces along the path, the source to the destination. Delay, the cumulative sum of all interface delay along the path in tens of microseconds. Reliability represents the worst reliability between the source and the destination, which is based on keep alives. Load represents the worst load on the link between the source and destination, which is computed based on the packet rate and configured bandwidth of the interface. How do we find these bandwidths? As I said earlier, show interface, okay? And when we would actually care about these bandwidths, when we redistribute one routing protocol into the other, such as OSPF into EIGRP. When we redistribute OSPF, we have to put what the bandwidth of we have to put all this stuff in so that EIGRP can calculate the external metric, because we saw that it has all that information in it. Okay. But anyways, it has bandwidth, delay, reliability, TX, and RX, right? Which the TX and the RX apparently are the reliability. Are they not? No. Reliability, TX and RX transmit, receive. Anyways, on this TX and RX, they are, reliability is almost always 255. I don't know when these actually change. I've never seen these change in the ones that I've configured. Anyhow. Goes back to configuring the bandwidth perimeter. And where do we do that? On serial interfaces, right? For it to calculate correct bandwidth, we put it on there. So there's our delay. It's a default, right? So Ethernet, we have 1000. Faster Ethernet, 100. Gigabit 10. The slower, the bigger the number. I think that makes sense because it's delay. So how do we so if you want to know how we can take this number and break it back down into the metric, we could do that. I don't know when you'd ever want to do that, but I guess it's important to know how it's done, right? So 10 million divided by bandwidth plus sum of delay divided by 10, or added together, both those added together, and then multiplied by 256 equals metric. Woo! That's why we get such a wonderful number. Alright, you guys can calculate that now. Alright, now, here's the hardest part. And apparently, my screen's all messed up. But we have dual concepts. So dual provides loop-free pass, loop-free backup, paths, which can be used immediately, fast convergence, minimum bandwidth usage with bonded updates. Okay, so we have a successor. Remember, that's the route, that's our primary route. That's what goes into the routing table. So if we do a show IP route, if we see that in there, it's a successor. We have a feasible distance, right? So that's the metric that we're calculating. So it's how far, I don't know, in my words, it's how far a router thinks it is from another router. We have a feasible successor, which is a possible backup route, which it has to meet feasible condition, which is down here, to be a feasible successor. There are routes that can't be a feasible successor, but feasible successor is just a route that would go up instantly if we thought it was closer. So then we have RD and AD, and so in our EIGRP topology, our first number is the feasible distance, then we have reported distance or advertised distance. So what another neighbor has told us how far a route is. So how far we think it is, how far we've been told it is. So that's what we're going to be studying. This is the hardest part to understand of EIGRP. All of it, like programming, is pretty simple. I mean, use bandwidth delay. Those are, I guess that's a little confusing, but at the same time, feasible condition is usually the hardest to get. And I don't know. Feel free to read that. I want to get to the good stuff. Okay. So feasible successors are backup routes, basically, right? But they're a backup route that goes up instantly. So dual can converge quickly using feasible successors. A feasible successor is a neighbor that has a loop-free backup path to the same network as the successor and satisfies the feasible condition. The feasible condition is just making sure that that feasible successor is a loop-free loop, okay? And so feasible condition says something. So the feasible condition is met when a neighbor's reported distance, alright, so that's the second number we're going to see in the topology, is less than the local router's feasible distance to the same network. Okay, so because it's what the feasible distance is what someone else is telling us, it should be less than the feasible distance of our current primary route. And so that's what feasible condition is. You can be a feasible successor if your feasible distance, or your reported distance is less than the feasible distance of the successor. Okay, so successor is a primary route. You can be a feasible successor if your reported distance is less than the feasible distance of a successor. If the reported distance is more than the feasible distance of the successor, then it might not be a loop-free loop. And so that's where it gets confusing. So where else are we going to see the feasible distance? That's our metric, right? And so when we do show IP route, that's going to show us our feasible distance. But then we get, nope, they're not showing us our topology table yet, right? Okay, so in the topology table, we see all of our routes. And then we have our dual states. So this is basically the dual table, is what we could call it. It's the dual algorithm. And so if we have multiple routes, like right here, it's going to show us that. So this is, we could have a possible feasible successor here. We could have a possible feasible successor here. We could have a possible feasible successor here. This one, we don't. We just have one way there. Okay? So that's the things we know. And so then it shows us our feasible distance for that route, right? So if that's not a feasible successor one, though, so we will go to this one. So we have 21712. Okay, or, nope. It's not the feasible distance. Sorry. This is the feasible distance, alright? And so this is the current successor, one successor, right here. And we know it's the successor because it's the same as the feasible distance. So now, this actually could be this is a feasible successor because the reported distance is less than the feasible distance of the successor. Okay? And I know that's a lot, but if you read over it, it starts making sense. But it is a little confusing. Oh, back. So the P, what we're seeing here, the P, we have either passive or active. Second most confusing thing, right? So passive means that dual has been run and our route is converged. Active means the algorithm is actively running. So we aren't a converged network if we see an A there. But if we see a P, dual's ran, it knows what's going on. Right? So then we have our destination network, and it says one successor with a feasible distance. So as we saw before, here it is, feasible distance right there. 1, 2, 3, 4, 5, 6, 7. So once again, this other route could actually be a feasible successor. Now, if this started with a 400 instead of a 200, it would not. There would be no feasible successor. So just because we have 2 doesn't mean there is a feasible successor. Oops. Let's go back. Maybe it was going to show you the feasible successor. Yep, it's showing that it is a feasible successor, right? So first number of the show IP EIGRP table, feasible distance, or the metric of EIGRP. The second one's reported distance, which is only important for feasible condition, right? Okay. So this one, we don't have a feasible successor, right? As we see, the reported distance is larger than the feasible distance of the successor. Okay. That activity of determining the feasible successor would not be bad. Here's what happens if dual doesn't find a feasible successor, right? So if there is a feasible successor, basically, and the successor goes down, right? So the primary route goes down. If there's a feasible successor, it instantly takes the place of the successor. If there's not, then dual will run an algorithm trying to find another way to that route. If you can't find one, I guess it's just down. But either way, a feasible successor is better to have because it helps us keep that network uptime. Anyways. Now for version 6, where do we change? Well, just like with OSPF, we do very little in the IP version 6. In the IP version 6, like the router, we say IP version 6 router, right? That's our first change. Then we send router ID so that we have a router ID. And then here's the major change, right? The link local is where all of our updates are going to be sent to, right? FF02. It's going to hit the link local addresses of these routers. So that's what's going to take the updates. So our destinations when we're sending information is going to be FF02::A. The link local is going to be the source. Just showing our IP version 6 addresses, I guess. So configuring this thing. As I said, we say IP version 6. Nope, they're setting addresses. They're setting link locals. Well, that's no fun. Alright, so we'll keep going until we find our important commands. We say IP version 6 router, EIGRP2. Alright, they put IP version 6 unicast routing. Remember, we need that for any time we are going to allow IP version 6 unicast routing. Then we put a router ID. And they put EIGRP router ID, but I think we can actually just put router ID. And they said no shutdown. Alright, so then from there we go into the interfaces and we associate them with EIGRP by going in the interface and say IP version 6, EIGRP2. We don't have to put network, right? There's already a network built into the IP version 6 EIGRP interface. Alright. Then we could once again choose passive interfaces for the interfaces that go to switches. this that don't need any routing information. Remember, routing information is only important between routers. Okay, and all of our show commands, show IP version 6 protocols, are the same as EIGRP. What can we use to verify? Well, we probably use show IP version 6 route, just like we use show IP route. And then my other would be show IP version 6 or IP, depending on what version you're using, EIGRP topologies, and neighbors. Those are probably the primary, and then we might have to debug if we don't do that. Anyhow, that's our basic EIGRP for that chapter, and hopefully you had a good time. Send me an emails if you have any questions.